Hello everyone, this is part 4 of Applied Biostatistics. My name is Christoph Correll and we'll talk today about analyzing the data. First of all, it's very important to understand the nature of your data. That means, are they normally distributed? That means they follow somewhat of a Gaussian curve shape. They can be left skewed or right skewed. They can be uniform, bimodal or multimodal. And that would require then not our normal parametric statistics, but rather non-parametric statistics, because parametric statistics are based on the normality of the data. So visualizing your data is important. There are also tests in statistical programs to see whether the normality is true for the data or it's not true. You get a p-value for that. Again, for continuous outcomes, you would report means and standard deviations or standard errors, whereas for non-normally distributed data, you would use medians and then 75 to 25 percentiles in order to differentiate the data. For categorical outcomes, it's obviously the n, the number of patients, and the percentage of the entire group. Missing data are really tricky and important because we always have to make assumptions what would have happened if the patient stayed in. So the often used assumption is that patients who drop out don't get better. And then you carry forward that last assessment till the end. That's called LOCF, or last observation carried forward. The most extreme of that is to do BOCF, that's baseline outcome carried forward. So for people who don't even come back for their first measurement, you would carry forward their baseline score, which is the most conservative assessment, as if nothing would improve. Nowadays, we are getting away more from this assumption, last score is the one I carry through, and more mixed models are used, where you do imputation not with the last value, but basically you look at the slope of the curve or the change until somebody drops out, and then impute the data and values from people who had similar early changes, so that you are modeling this more as if you predicted based on commonality. Obviously, that assumes that there's somewhat a linear outcome and that you have more data that are not missing than data that are missing. Now, the simplest way is to just ignore missing data and only look at observed cases. That is generally seen as the weakest evidence because you may have very strong biases for one group to stay in treatment and the other one not staying in treatment. What statistical test you use, you can see in this table, is very simple. For categorical outcomes, you use the chi-square test, or if you have in at least one cell less than 5 patients, you would use the Fisher's exact test. That is, gives you basically it's a more conservative measure there. The t-test is the test for continuous variables that are normally distributed when you have 2 groups. If you have more than 2 groups, you would do an ANOVA. If you then add maybe baseline variable or something else into the analysis, it's called an ANCOVA because you're using covariates in that group comparison. However, if your data are non-normally distributed, then you would have for 2 groups to do a Wilcoxon rank sum test, and if there are more than 2 groups, a Kruskal-Wallis one-way ANOVA. When you look at the same group over time and compare it with itself, then you would do a paired t-test for normally distributed data, and for non-normally distributed data, the Wilcoxon signed rank sum test. And the Magna-Mars test would be for categorical dichotomous variables. How do you correct for multiple testing? Well, I mentioned in part 1 that ideally you have one main outcome, and you power it around that outcome that answers your question or tests your hypothesis. But you may have more than one question that you want to address. So you can do 2 things. You either say they are both equally relevant for me, and I test both at the same time. If you do that, you have to cut your alpha in half. So instead of having 0.05 as your p-value, you divide that by 2 tests, and that makes it 0.025. So it's harder to reach that goal, and you need a higher sample size in order to test 2 tests at the same time. But you could also say, the second question is not as important for me. I do a hierarchical testing. I surely will win on the first one, 0.05, and if I win there, I can look for the second outcome, and I still use 0.05. And you can do that 3 or 4 times until you reach the end. And you don't have the 0.05 assumption anymore. The risk is that maybe your second, third, and fourth one is statistically significant at the 0.05 level, but your first one is not. And then you're not allowed to look anymore, and your whole study is gone. You can also say, I use multiple testing for my 5 variables, and I divide 0.05 by 5, and then each of them would have to reach 0.01 as a statistical test, which again would increase your n dramatically. What's generally done is to have one primary outcome, maximum of 2, and then say the other ones are secondary outcomes. And you test them all at 0.05, but that is then more exploratory. And for the truly exploratory aims, you can do multiple tests and questions where you don't even know whether or not there is going to be a statistically significant outcome, but that will be pilot data, so to speak, for your next study to see what the effect size would have been. The simple division of number of tests, or dividing 0.05 by number of tests, is called Bonferroni correction, which some of you might have heard. Finally, correlations are being done either on normally distributed data with the Pearson correlation coefficient, or if it's non-normally, you would use the Spearman rank correlation coefficient. Then you might be interested in not one variable predicting or correlating or being associated with your primary outcome of interest, which is the dependent variable, but you might want to look whether several variables are independently correlated or associated with your dependent variable. For that, you do a regression analysis and fit multiple variables and their correlation with the primary outcome of interest. For a categorical outcome, you would do a logistic regression, and for a continuous outcome, you would do a linear regression. And then there are various ways of dealing with that. You can either put a priori certain variables into the model and ask which one will remain significant even when you control for variables that were not significant. Let's say you want to have male or female or age group in there. Or you can do univariable analyses with your primary outcome and only enter those variables that were significant in the one-to-one comparison. And then those that are entered either stay in and you see what is left over, or you do a backward elimination, always removing that variable that had the least significant level until you're only left with variables that are at a 0.05 variable significance level in your final model. And this would then be variables that are independently correlated at a significant level with your outcome of interest. Tricky is that you should only enter variables that are not highly correlated with each other, because they can otherwise cancel each other out. So if things are very much on the same dimension, you should only pick the one that had, in the univariable analysis, the best significance level. This concludes the fourth and final portion of our Applied Biostatistics program, and we leave you here with some useful online calculators that you can use in order to ask questions or do certain analyses. And we hope that this program was helpful to you.